Welcome to the RVU OMM Mechanisms of Action series. This edition will look at the proposed mechanism of action of counterstrain technique. An understanding of muscle physiology is essential to explaining the proposed mechanism of action of counterstrain technique. So let's review the relevant aspects of physiology first. Skeletal muscle is composed of bundles of extrafusal muscle fibers. These are innervated by efferent alpha motor neurons in the ventral roots of the spinal cord, and are supplied with afferent sensory nerve fibers which travel in the dorsal spinal roots, specifically group 1A and group 2. There are also fusiform or spindle-shaped intrafusal muscle fibers that are parallel to extrafusal muscle fibers. Each end of the intrafusal muscle fibers are attached to extrafusal muscle fibers. This parallel orientation ensures that as extrafusal muscle length changes, a simultaneous change is experienced by the intrafusal muscle fibers. The length of the intrafusal muscle fibers are regulated by the gamma motor neuron. There are three monitoring systems of skeletal muscles relevant to counterstrain technique. The first are Golgi tendon organs, which monitor tension and muscle force. The Golgi tendon organs are in series with the extrafusal muscle fibers and lie within muscle tendons. Afferent group 1B sensory nerve fibers carry the impulses from the Golgi tendon organs to the spinal cord, which then affect an interneuron, which then activates an alpha motor neuron of the same muscle. This allows the Golgi tendon organ to inhibit muscle contraction when it senses excessive tension of the monitored muscle to prevent muscle injury. The remaining monitoring systems are proprioceptive and located within the intrafusal muscle fiber spindles. One system consists of annulospiral endings, which send proprioceptive information, specifically length and rate of change in length, to the spinal cord via group 1A afferent fibers. The second system consists of flower spray endings, which send proprioceptive information, specifically stretch and absolute length, to the spinal cord via group 2 afferent fibers. Now that we reviewed that, let's get back to counterstrain technique. There are three proposed mechanisms. The first is proprioceptive. Tender points develop when local muscle fibers are maintained in a hypertonic state due to an inappropriate proprioceptive reflex during the initiation of somatic dysfunction. As an agonist muscle is suddenly lengthened, its intrafusal muscle fibers are also stretched. To avoid injury, the agonist muscle reflexively contracts through a defensively initiated protective reflex activation of alpha motor neurons. The contraction of the agonist muscle results in a sudden lengthening of the antagonist muscle. This may cause reflexive contraction of the antagonist muscle. Altered motor neuron activity maintains the two opposing muscle contractions, leading to tender points in either or both muscles. Shortening myofascial tissues associated with the tender point reduces the somatic dysfunction's nociceptive input to the central nervous system, thereby normalizing the neurophysiological activity, myofascial tone and length, and local circulation. The second is sustained abnormal metabolism. Tissue injury alters local body position, affecting local microcirculation and tissue metabolism. A localized ischemia can result, and local nutrient supply and metabolic waste removal are reduced. Pro-inflammatory cytokine production is increased. These changes lower the firing threshold of sensory neurons, causing localized neuronal sensitization. The changes manifest during palpation as localized edema and tenderness. The precise body positioning in counterstrain improves local vascular circulation and reduces localized production of inflammatory mediators. The third is impaired ligaments muscular reflex. Dysfunction may result from a protective reflex that occurs when ligaments and related myofascial structures are placed under strain. A localized strain in a ligament can reflexively inhibit muscular contractions that increase the ligamentous strain while stimulating muscular contractions that reduce the strain. Shortening myofascial tissues associated with the tender point reduces the somatic dysfunction's nociceptive input to the central nervous system, thereby normalizing the neurophysiological activity, myofascial tone and length, and local circulation. All right, so now you know how counterstrain technique works. And remember, as A.T. Still says, an osteopath reasons from his or her knowledge of anatomy and physiology. This has been an episode of the RVU OMM Mechanisms of Action series.